Before I start, I'd like to do a little nationalist preening. One of the things you'll note I come back to over and over is that a lot of foundational work in geospatial technology happened in Canada. And I think there's three reasons for this. First, Canadians are just objectively awesome. Second, Canada has a lot of land, and most of it's owned by the Crown, so the government was an early adopter and funder of geospatial technology, and remained so for a generation. And third, just luck and locality. Particularly in the early internet days, there was still a premium on being physically co-located with other domain experts. And in the case of Victoria, Canada, the intersection of being in a government capital, of a natural resource-intensive province, when geospatial was still rapidly innovating, created a local population of awesome Canadians who were able to do a bunch of cool things and see they were cool because they were relevant to us and to our local professional circles. Anyways, I'm not going to bury the lead. Location matters. Canada rocks. So, history. Working in software, right, where the state of the art can become obsolete in a handful of years, history is a difficult subject. It is even worth talking about history of something as incorporeal as software. Software is something we experience. It exists in real time as it acts and reacts to the stimuli we produce for it. And absent a whole infrastructure of electricity and electronics and peripherals, the software itself simply disappears. The practical lifetime of most software is measured in a handful of years. PostGIS is quite rare for still remaining relevant after 23 years. And software is no marble statue, it's no fresco, but it does share some features with art and music. Software is responsive to the context around it. Software builds on the software that came before. The best, and frequently the most popular, software anticipates the needs of society before society quite understands the needs itself. Think VisiCalc, think open source and Linux. Today's software is a product of yesterday's software, so knowing where it came from can be useful, or at least entertaining. I came to this topic, the topic of software history, because a couple months ago, Chris Tucker, the chair of the American Geographic Society, wrote me an email out of the blue asking me, what was the first spatial database? And I kind of thought, that's easy. And then I thought, because, what's a spatial database? It's a question very much in the vein of, have you ever really looked at your hand, man? Really looked? The more you stare at it, the stranger it looks, the more the parts don't really make sense in relation to one another. What's a spatial database? What's a spatial database? Is this a capabilities question? Is this about what software does? Because if it's about what the software does, then a spatial database is a piece of computer software that manages spatial and attribute information together and allows you to query that information using spatial or attribute filters or both at once, right? Except by that definition, the first spatial database was the Canada Land Inventory System from the 1960s, the system that resulted in Roger Tomlinson being dubbed the father of GIS. The Canada Land Inventory System definitely had both spatial and attribute information about soils in Canada, and it could query that information both spatially and non-spatially. It could also display maps and do printouts, but I don't think our definition of a spatial database is a GIS but without the maps. That'd be a pretty sucky piece of software, not one worth doing history for. So the Canada Land Inventory System, that was the first GIS, but not the first spatial database. And the first spatial database was not a GIS. Instead, the identity of the first spatial database is bound up with the lineage of the first databases. And I think it's the database part that's key. There's also a missing word in the original question, relational. Relational databases are general purpose software suitable for storing and searching large collections of any kind of data. And when we talk about spatial databases, we're talking about relational, or very relational-like databases. Relational theory says that a single fact or entity can be modeled as a set of named values called a tuple. And relational theory says that a collection of facts can be modeled as a list of tuples called a relation. And relational theory says that a system can be modeled as a set of interrelated relations. So, relational theory defines a general purpose architecture for modeling any system. Hotel reservations, balance sheets, sports scores, recipes, tax returns, they can all be modeled as collections of relations. And so, one step further, relational theory says that a general purpose engine can be built to efficiently access and manage data in a relational model using a declarative language. The relational model allows general purpose data management software where you can access and alter custom structures of data without ever writing custom code. And let's be clear, relational theory was right. If you want to store and access data these days, you use a relational database. The most widely used database in the world is SQLite, a relational database that's embedded in every cell phone as the storage layer in mobile programming APIs in web browsers. The paper that started the relational database revolution was A Relational Model of Data for Large Shared Databanks by E.F. Codd, who worked at IBM Research, and it came out in 1970. This was the starting gun for the relational database race. To make Codd's theoretical system a reality, the first relational database implementations all started in the 1970s. System R, that was started at IBM right after the Codd paper, and eventually fully commercialized as DB2, which is still with us as a niche enterprise database. Oracle was founded in 1977, and it still stands astride the industry in many ways. And most importantly to us, as PostGIS people, Ingress was started at the University of California, Berkeley in 1973. Ingress. Why is Ingress important to PostGIS and Postgres people? Ingress is important because Ingress was started by a computer science professor named Michael Stonebreaker who wanted to prove out Codd's model in the real world. And Ingress is important because it was only the first of his many forays into writing databases that test theories of computation in the real world. Ingress was commercialized by Stonebreaker and others in the early 1980s, and developers from Ingress went on to found Sybase, which was in turn used as a foundation for SQL Server by Microsoft. It's amazing how the database world is based on these lineages of things related to Ingress, and it gets even more crazy when you look at the next thing Stonebreaker did. Because by the time Ingress was commercialized in the 1980s, Stonebreaker felt that he'd proved out the relational model, but that the model itself had some obvious potential points of improvement. And so he proposed a new project called PostGIS. Just as PostGIS Day comes after GIS Day, Postgres comes after Ingress. Stonebreaker laid out his plan for Postgres in a 1986 paper, The Design of Postgres, and he proposed the following goals. Provide better support for complex objects. Number 2, provide user extendability for data types, operators, and access methods. Number 3, provide facilities for active databases, alerts, and triggers. Number 4, simplify the database code for crash recovery. Number 5, produce a design that can take advantage of optical disks, workstations composed of multiple tightly coupled processors and custom designed VLSI chips. And number 6, make as few changes as possible, preferably none, to the relational model. For a paper from the 80s, it really nailed what was going to be important going forward, with the exception of optical disks and VLSI chips, which were just mid-80s buzzwords. The first two items, complex objects and user extendability of types and access methods, which is just a fancy word for indexes, those two items are really the key capability that made PostGIS possible. But I'm getting ahead of myself. So, in the mid-1980s, Stonebreaker kicks off the Postgres project, and it chugs along for just under a decade, building out the working core that does all the things in the original paper, except for those pesky optical disks. As he did with Ingress, Stonebreaker took the Postgres source. In 1992, he created a company, Illustra, to commercialize the technology. Illustra never really catches fire, and it's eventually acquired by Informix, which is itself eventually acquired by IBM. And you can still buy an Informix Universal Server from IBM that includes pieces of the original Postgres from Illustra. More importantly for us, Something's different in 1993 when the PostGIS project ends. Different than things were in 1980 when Ingress wrapped up. By 1993, there's this internet thing. It's connecting people. It's giving them access to free software. The PostGIS source was made available to other researchers in 1989, so they could experiment with all the cool new features, type extension in particular. So when Stonebreaker ended the academic PostGIS project in 1993 to go pursue Illustra, he also orphaned an existing user community who were using the system for real work. Rather than letting the software die out, 2 Berkeley graduate students, Andrew Yu and Jolly Chen, continued development of PostGIS for a couple years. And in 1995, they released PostGIS 95. PostGIS 95 replaced the old PostQuel language with standard SQL and added lots of production and stability improvements. In 1996, Chen and Yu moved on, but the development didn't cease. It was picked up by an international group of users, some of whom are still developing PostGIS to this day. There's my Crunchy Data colleague Tom Lane in this transitional picture that includes Yu and Chen and some of the original open source team. So, okay, what's the point of all this? The point is that, circa 1995, you have quite a few relational databases. You have first-generation databases like Oracle and Ingress and DB2. You have second-generation databases like Postgres and Informix and Sybase and SQL Server. You have some proprietary branches like Illustra. But do you have spatial databases in 1995? You have a number of kludges that store spatial data in the database, but keep the smarts about how to use it outside the database. Like the old Esri SDE software, that's a notable example of this model. You have a database process and an SDE process, and the clients connect to the SDE process in order to do anything spatially oriented. The geometry is stored in opaque blobs that only the SDE process can understand, and the indexing is a grid index that only SDE manages, and so on. The only advantage of the GIS server kludge is that it allows GIS companies to sell GIS server technology that works against multiple relational databases, because the actual feature set of the relational database is barely used. It's just a dumb storage box for the GIS engine. And frankly, amazingly, this model persists in the confusingly named Enterprise Geodatabase. That's it, it's deliberately confusing, which achieves database independence for the Esri ArcGIS client by layering a bunch of structure onto the data model that can only be managed by Esri ArcGIS client software. It's a cute trick. It's not a spatial database. But moaning about Esri is for beers later. When I sat down for beers with my geospatial buddies back in the early 2000s, what we bitched and moaned about was Oracle, who absolutely dominated the local tech industry in Victoria at the time. And, they would sometimes say things, oh yeah, Oracle Spatial was invented in Canada. And I would go, yeah. Because of course, all good things geospatial were invented in Canada. That's pretty much an article of faith. I mean, you've heard about the Canada Land Inventory and the father of GIS, right? Right? But they would insist that it was true, that the Canadian Hydrographic Service had invented a thing called an HH code, and they used it to index all their millions and millions of bathymetric sounding points, and that Oracle had come in and hoovered up the people, and then released the tech as their own. And I would go, yeah. And that was kind of the end of it. The end of it, that is, until Chris Tucker asked me what the first spatial database was. And I wondered, is there anything to that HH code story? And it turns out there is. In the late 1980s, 2 Canadian Hydrographic Service employees, Hank Boudreau and Herman Varma, came up with the HH code, which is basically a glorified Z-curve or Morton curve supporting higher dimensions and with some metadata tacked onto the end. You see where the HH and HH code comes from? The first paper they wrote calls it a hydrographic hyperspatial code, and the Oracle press release calls it a helical hyperspatial code, but I think we all know it's a Hank Herman code. At some point, Hank and Herman contacted Oracle because they needed to get some native functions into Oracle, and unlike Postgres, Oracle was not built with user-level type extension in mind. Oracle was intrigued, though, and they set up a development center in Hull, Quebec, and Varma was seconded there. And so in 1995, at the GIS 95 Symposium in Vancouver, Oracle announced the Oracle 7 multi-dimension package, for Sun Solaris, Digital OSF1, and HPUX, starting at $6,510 Canadian dollars for an 8-user license, featuring the rechristened helical hyperspatial code driving their spatial index. And you know what? Small world, I was actually in Vancouver attending GIS 95. Not that I knew anything about Oracle or spatial databases at the time. I was attending as a policy analyst with an interest in making geospatial data available to indigenous governments. But I was there at the beginning, the first spatial database integrated into a commercial relational database in 1995. Except, wait a second, Oracle wasn't the first. It was just a big deal because Oracle was a big deal. Actually, you can find references to the Illustra spatial blade that date back to 1994. And the spatial blade is doing a lot more than just indexing points with a Z-curve. It was modeling lines and areas too, and had an archery index. Except, wait a minute, why are we focusing on commercial databases here? I found a copy of the PostGIS source code from 1994. This would be after the academic project wrapped up, but before the PostGIS 95 release. And right there, where I expected to find them, are the original PostGIS spatial types. Point, path, box, polygon, and an archery implementation to index them, no kludgy Z-curve, a modern spatial database implementation from before 1994. And so it's not surprising Illustra had the spatial blade in 1994 because Illustra was a PostGIS fork, and PostGIS already had spatial types. The first relational spatial database was PostGIS. I haven't tracked down any earlier source code, but the implementation was sometime before 1994. So the scene in 1995 is a bunch of relational databases all competing. The big ones are Oracle and DB2 and Sybase. There's a bunch of kludgy spatial servers like our Esri SDE and MapInfo Spatialware sitting on top of them. PostGIS isn't released until 2001. So what happens in the 6 years in between? Amazingly, almost nothing. The two big events in the spatial database world are the release of the OpenGIS Simple Features for SQL Standard in 1999, and the release the same year of Oracle 8i Spatial, which was very much informed by that standard. Now, the standard had 5 editors from Esri, IBM, Informix, MapInfo, and Oracle. And of the 3 database companies who wrote the standard, only Oracle released a relational spatial database of its own. Informix eventually got there by purchasing Illustra and rebadging it as the Informix Universal Server. The other thing that happened after 1995 is that I started an IT consulting company in 1998. In 1998, there was just the one of me. By 2001, there were 5 or 6 of us. And in this picture, it's from around 2004. I had learned geospatial on a contract with the British Columbia government on a data analysis system developed in British Columbia called Facet. The crazy thing about GIS 95 and the 90s in GIS, which I remember, was just how many different GIS companies there were at the time. There was a brief flowering of locally built GIS systems in every marketplace, a pre-Cambrian GIS explosion as the capabilities of computers surged upwards and it became possible to run a GIS on commodity hardware. Initially on the new workstation class Unix systems from HP and Digital and Sun, but then on consumer PCs a little later. Facet was one of those regional GIS software companies based out of Vancouver. And then the Esri asteroid landed in the 2000s and wiped it all out. By 2010, everything was standardized and local development was quite rare. Anyways, in 1999, we worked using Facet on a big GIS processing contract for the British Columbia Ministry of Environment. They wanted to take every third-order watershed in the province, about 20,000 of them, and calculate several dozen environmental metrics for each watershed. Things like the lengths of roads in the shed, land cover classes in the shed, amounts of steep slopes, old forests, and that kind of thing. This was, for the time, a huge amount of processing, hundreds and hundreds of hours. Facet only ran on Sun workstations and wasn't 100% reliable. Sometimes it would crash or run out of memory, so we had to build a custom batch control system to keep all the workstations busy while recovering partial calculations and saving intermediate state to allow restarts and to work around crashes. And what sat at the center of that batch control system? A relational database, PostGIS. By the end of the processing, we not only had the numbers for every shed, we also had all the source data clipped to each watershed and the derived data too. But the only way to interact with it intelligently, the only way to ask spatial things of it was via facet. And that seemed really dumb, like really limiting. It would clearly be very cool to use the same SQL we use to manage the batch control to run custom summaries on the process data. However, we had consulting to do and software development was not really our bag. And then two things happened that changed the calculus. First, on April 1st, 2001, the fiscal year ended, as it always does. And so all our government contracts ended, as they always did. And as it turns out, we only had contracts with the government. That was our only customer. So actually, all our contracts ended. But this was normal and expected. Like, we often took vacation in April, precisely because there was nothing much else to do. But then the second thing happened. There was an election, and the government changed. The new government came in promising to review everything government did and cut back anything that wasn't core. This core review was going to take months. And in the interim, the civil servants just sat on their budgets and didn't sign any new contracts. All our new contracts were over. No new contracts were coming. What to do? Being young and free-spirited, we decided that the thing to do would be to explore technology so we could hit the ground running when government started up again. It had to start up again at some point. Maybe there was going to be a market for this new Oracle spatial database stuff. And I spent some time taking meetings and learning that actually there was nobody in government who wanted it. The non-spatial ministries didn't see the point, and the spatial ministries already had their kludges in place, and they weren't interested in modernizing. It would be cool to learn about spatial databases, but we couldn't afford Oracle Spatial, certainly not without a customer to bill in the days before free developers versions existed. But maybe we could put some open source database to work. And here it's worth noticing we had some options. It would have made a lot of sense to add spatial capabilities to MySQL, the most popular open source database at the time. But MySQL had the same problem that forced the Canadian Hydrographic Service to go to Oracle when they needed its native spatial functionality. MySQL was not built for user extension. Adding a spatial type required a lot of knowledge of MySQL internals and caused changes across the whole code base. And we know this because we reviewed the patch a couple years later when MySQL finally did release spatial functionality. It was a complex patch. We wouldn't have been able to do it. And so we looked at Postgres. Now remember, at this point, 2001, Postgres already had core spatial features. It had path and point and polygon types. Why did we need PostGIS? Because the spatial features in Postgres were built for computer graphics, not for GIS. The polygon type didn't have support for holes. None of the types supported aggregation, multipoint, and that kind of thing. The maximum size object was determined by the page size, 8 kilobytes, which meant they could only hold a few hundred vertices. GIS objects are routinely far, far larger. Those are the things we knew. The things we didn't know, but would have learned, were things like submitting software directly to the Postgres project would have put us on a very slow release cycle, exactly when we wanted to be on a fast cycle at the start of the project, when we were adding new functionality every day. Our eventual use of GIS as our computational geometry engine and Proj as our reprojection engine, that would not have been allowed, as Postgres doesn't have C++ dependencies. In general, Postgres has very few dependencies, and depending on a huge library like GIS, might never have been accepted. Basically, adding spatial was a messy affair, and the Postgres project is a fastidious, clean project. So PostGIS was built as a Postgres user extension, just as Michael Stonebreaker had originally visualized back in 1986 in the design of Postgres. For the first 2 years, almost all PostGIS development was done by Dave Blasby. And to give you a sense of the messy affair it was, he worked primarily on Windows, using Notepad as his code editor. And then he compiled the code in Solaris on our Sun Ultra 10 workstation, because Postgres was Unix only at the time. For the first couple months, the code was not version controlled, and Dave managed changes through the classic method of taking full copies and renaming directories. But PostGIS was moved to a CVS revision control system on June 22nd, 2001. Amazingly, we have source control logs from then, right up to the present, 23 years of them, having migrated from CVS to Subversion and then on to Git. The 0.1 release came out on May 31st, 2001, and had OpenGIS standard types, point, line, polygon, multi-point, multi-line, multi-polygon, geometry collection. I had an R-tree index for those types and 11 functions. Endpoints and rings, mem size, num sum objects, summary, length 3D, length 2D, area 2D, perimeter 3D, perimeter 2D, and truly inside. Note that there's only one function that actually has two geometry parameters that returns a spatial relationship, the truly inside function, which really should have been named point and polygon because that's all it tested. Incredibly, we have a complete mailing list archive from the initial release in 2001 up to the present. And so from there, we can see that it was the legendary Canadian Frank Warmerdam, the founder of the Google project, who suggested only 3 weeks after release that we stop making up function names and instead use the Simple Features for SQL document as a guide. I'm reviewing the OGC SF-SQL effects specification, and I'm wondering about how closely you were interested in following it. In my dreams, PostGIS would implement a useful subset of SF-SQL types and functions in a manner that would make it relatively easy to port applications between this environment and other environments claiming to implement SF-SQL. Haha, a wonderful thought. But of course, Oracle never bothered to follow the SF-SQL function naming conventions. And it took another 15 years for Esri to allow SQL to be used to query data in their tools. But it was a nice thought on Frank's part, and we did start following the SF-SQL guide from then on. The idea that Frank Warmerdam was interacting with us within 3 weeks of release is pretty crazy. But it didn't stop there. A Canadian, Danielle Morissette from the Map Server project was on the list right away. James McGill from GeoTools was on the list within a couple months. The other two longest serving PostGIS contributors, Regina Obey shows up in November of 2001 and Sandro Santilli in November 2002. Gary Sherman from QGIS shows up in 2003. In retrospect, in 2001, we had a lot of spare time, thanks to the ongoing slowness of government consulting that first year. And as a result, there were a lot of PostGIS releases and a lot of time spent incubating community. 0.1, the May 31st, 2001 initial release. 0.2 came out in June, weeks later, with well-known binary support and documentation. The 0.5 came out in July with a pile of OpenGIS functions. Native PostGIS support and Map Server came out in August. 0.6 came out in September with another pile of functions. So that's just 4 months. Then things finally start to slow down. 0.7 came out in May 2002 with coordinate transforms. At this point, all the easy functions from the Simple Features for SQL were done. And we were staring at the hard ones, scratching our chins. Union, intersection, buffer, touches, and all their friends. It's very easy to find algorithms for area and distance, and it doesn't require a lot of complexity to implement them for the simple features. The constructive geometry functions, union, intersection, buffer, and the more fine-grained Boolean predicates, those are a completely other story. Fortunately for us, even before PostGIS was a glimmer in our eye, a separate project had also started, also in Victoria, more Canadians. And this is where locality really matters. Victoria is the capital of British Columbia. It's where a lot of geospatial smarts of government resided and where a civil servant, Mark Sondheim, worked. The department Mark worked in managed large data sets, and he expected there was going to be a need for programmatic data processing of these huge data sets, which meant there was going to be a need for a basic library to represent that data in simple features form. And rather than sort of cross his fingers and start writing Avenue code or dusting off his Esri skills, Mark tracked down Canadian federal government funds and contracted with a local Victoria company to write that core library, a Java implementation of the simple features specification that was going to be called the Java Topology Suite, JTS. And working at that company and assigned to the project was one Martin Davis. More Canadians, more local Victoria, British Columbia content. Martin started on JTS in the fall of 2000. So JTS was actually in flight before PostGIS was even an idea. JDS was supposed to deliver in a year, but it took somewhat longer, and JTS 1.0 was released in February of 2002, less than a year after the first PostGIS release. So in early 2002, there was a working code base that had all the algorithms we needed to complete simple features for SQL in PostGIS. All the algorithms ready to go. Just one problem. It was all in Java. PostGIS and Postgres are written in C. C code cannot directly use algorithms in Java. However, C code can use C++ algorithms, and there's a lot of structural similarity between Java and C++. So translating the code from Java to C++ could yield the same algorithms, but callable by PostGIS. The trouble is, that translation would have to be manual. It would take a lot of expensive work by humans. More Canadian content. We needed money to fund a C++ developer, and it couldn't be one of our staff because by now the government was open for business again, and the staff were working on actual projects. So I needed to shake the money tree. I found a British Columbia Technology Fund that would provide dollars for technology development if the development was a partnership between industry and academia. So I went to the University of Victoria, and I found a professor with a student who wanted some project work, and we hired that student using those British Columbia Technology Funds, and so the GIS project was born, a project to port the JTS algorithms from Java to C++. The first GIS committer was Yuri Bishkov, a UVic computer science graduate student. Yuri's first commit was in June of 2002, and in November of 2003, a year and a half later, the PostGIS 0.8 release was the first feature-complete release of PostGIS with full simple features for SQL support. That was it. PostGIS was done in 2003. The 20 years since have just been a long denouement. Just kidding. I mean, the 20 years since Spatial became a standard feature for all relational databases. MySQL released Spatial in 2003. SQL Server added Spatial in 2008. Cloud databases like Redshift and BigQuery added Spatial in 2019. Even embedded databases like SQLite have Spatial. The idea that you can manage and query Spatial directly in a relational database without bolting GIS software on top is totally mainstream, except maybe among GIS users. Meanwhile, PostGIS has gone far beyond the simple features for SQL baseline, with geography and raster and linear referencing and vector tiles and JSON, over 300 functions for spatial processing. The speed with which PostGIS grew from that first release, that speed to me is indicative of just how much latent demand there was for the capability. It just makes sense to manage spatial data next to non-spatial data in a general purpose storage and execution system. If we hadn't built PostGIS in 2001, someone would have built it in 2002, and that thing would have taken off just as fast. It has been an incredible ride and a great deal of fun, and I'm glad you've all been on it with us. Thank you very much.